Continuing on to example 1, we want to A, find the currents through each of the parallel resistors given our source current is equal to 28 amps, B, the equivalent resistance of our resistor network, C, the voltage potential across a network if, for A through C, resistance of R1 is equal to 0.5 ohms, resistance of R2 is equal to 0.25 ohms, and resistance of R3 is equal to 0.125 ohms. And then we want to verify the conservation of power is maintained. To begin, we recognize our source, IS, is supplying current or a uniform voltage potential to R1, R2, and R3, which exist in a parallel configuration. Thus, we have three resistors in parallel. And there's two ways we can solve for our current. We could make our last two resistors, R2 and R3, an equivalent, such that Req would be equal to R2 times R3 per R2 plus R3. And then we can solve by placing the equivalent within our numerator per R1 plus our equivalent times our source current. That's a little messy. So we'll introduce a method via conductance. To solve for I1, all we need is the conductance G1 per equivalent conductance GEQ and multiply this by our source current. Doing such, I1 would be equal to our conductance G1, which is 1/2 ohms to the minus 1, per our equivalent conductance, 1/2 ohms to minus 1 plus 1/4 ohm to minus 1 plus 1/8 ohm to minus 1 times our source current. That is, I1 is equal to G1 per G2 plus G3 plus G1 itself, or 2 Siemens per the quantity 2 plus 4 plus 8 Siemens, or 2 per 14 times 28 amps. Therefore, I1 is equal to 4. Employing the same methodology, I2 would be our conductance G2 per equivalent conductance, which would be 4 per 14 units of Siemens cancel out, times 28 amps, or we'd have 8 amps flowing through I2. Last but not least, I3 would be found by having our conductance G3 in the numerator per equivalent conductance, or 8 per 14 times 28 amps is equal to 16 amps. Now it's noted, R1 has the highest resistance, R2 is in the middle, and R3 has the lowest resistance. Less current flows through R1 due to the higher resistance, and more current flows through R3 due to the least resistance. That is, we say, our current takes a path of least resistance. Now, if we want to find our equivalents, we can do such by multiplying, say, R2 times R3 per R2 plus R3, making one equivalent resistor, and then making an equivalent out of R1 in that prior equivalent. That is messy and cumbersome, so we will find our equivalent resistance through our conductance. That is, our equivalent conductance would be equal to the conductance of resistor 1 plus the conductance of resistor 2 plus the conductance of resistor 3. Or equivalent conductance is 14 Siemens, as was the term in our denominator when we solved for I1, I2, and I3. Therefore, our resistance is just 1 over our conductance. That is, our equivalent resistance is 1 over equivalent conductance, or 1 per 14 ohms. Now, if we want to determine our voltage potential across our circuit network, we can use our equivalent conductance and Ohm's law. That is, our voltage is equal to our current times our resistance, i.e. our source current times our equivalent resistance, which is equal to our source current times 1 over our equivalent conductance. That is, our voltage potential is 2 volts. To ensure our circuit maintains our conservation of electrical power, we first have to look at the power dissipated by each resistor, sum those up, and verify that our power dissipated is equal to our power supplied by our current source. Our power dissipated by element 1 can be expressed as our current times our voltage, or our current squared times our resistance, where I1 was equal to 4 amps and our voltage potential was equal to 2 volts. We could say that our power dissipated is also equal to our current squared, i.e. I1 squared, or 4 amps squared, times R1, 1/2 ohm. We see, regardless of the method used, that our power dissipated is equal to 8 watts. Our power dissipated by element 2 follows the same formulation. It can either be our current times our voltage or our current squared times our resistance. And our power dissipated by element 2 is 16 watts. And our power dissipated by element 3, solved via I times V, or I squared times R, is 32 watts. If we sum up our power dissipated terms, we'd have our power dissipated by element 1, 2, and 3 summed algebraically, which gives us 56 watts dissipated. Our power supplied by our current source is simply our current, IS, times our voltage, which is 28 amps times 2 volts, or 56 watts supplied.